ever see those crazy videos, tools running at incredibly high feed rates, and wonder how they do that? I'm going to explain why it works and how you can do the math and apply it in your applications. The key principle behind high-speed, high-feed machining is chip thinning. In this video, I'm going to explain radial chip thinning. At the center line of the tool path, the chip thickness equals the feed per tooth. But as the flutes pass center, the chip gets thinner and thinner until it exits the cut. If you reduce your width of cut to less than half the diameter, the chip thickness is less than the programmed feed per tooth. If you don't compensate for it, you'll be feeding slower than you should be, and worse, rubbing the tool instead of cutting, causing faster tool wear and less efficiency. Here's an example. Take a 1/2-inch 4-flute end mill running at 400 surface feet and 4 thousandths feet per tooth, and a 50% radial engagement. At that engagement, the chip thickness is 4 thousandths. Now, reduce the width of cut to 10% of tool diameter. Your 4 thousandths feet per tooth now produces a chip that's roughly 60% less than the 4 thousandths. You need to multiply your intended chip thickness by 1.7. To get a 4 thousandths chip, you need to feed it almost 7 thousandths per tooth. If we go to an even smaller step over, a 1/2 inch at 5% or 25 thousandths with the cut, 4 thousandths feet per tooth would feed around 50 inches per minute if chip thinning doesn't exist. Now you need to multiply the 4 thousandths by 2.3.
With chip thinning factored in,
The correct feed jumps to 112 inches per minute. That's more than 2 times faster with proper cutting pressure, less rubbing, and thus better tool life. The other factor to be considered is heat. The greater the radial engagement, the greater the heat. So when you're using a 10% radial width of cut, surface feet should be doubled to get the right amount of heat. After you apply the speed multiplier, the new feed rate is 170 inches per minute. At 5% step over, the feed rate goes from 112 to 220 inches per minute, compared to the conventional cut at 50. These principles are especially critical in high-efficiency milling with light radial step over, where the tool is only engaged a small portion of the material. Without compensation, these tool paths run far below their potential. Most modern CAM software includes a built-in chip thinning adjustment, but it's still important to understand the geometry behind it. Knowing why these numbers matter lets you verify tool paths, make quick manual corrections, and adapt when software defaults miss the mark. Radial chip thinning isn't just about speed, it's about balance. It allows you to fine-tune your feed to match your radial engagement, ensuring every flute cuts efficiently and every chip carries away the right amount of heat. In short, it's how you turn safe feeds into optimal feeds. Faster, cooler, and more consistent. In the next video, we'll look at variable pitch and variable helix tooling, where the focus shifts from chip geometry to vibration control. How the spacing and helix of each flute can eliminate chatter and make your cut smoother and quieter. As always, if you like the content, please like, share, and subscribe, and look for new videos each week with more performance tooling secrets.